used given thermodynamic diagram in order to find especially the specific enthalpies of all the characteristic points of the vapor compression cycle. Then we can do a proper energetic analysis that is calculating the power that is exchanged in each of the characteristic devices exchanging energies. So we have two heat exchangers, the evaporator and the condenser, and then we have one device that is receiving a technical work that we need to pay to make it work. That's the compressor receiving technical work. So let's start with the heat transfer we have in the heat exchanger. So if we start with the Q coils, so the heat transfer we have in the evaporator, so with the coil source. In this heat exchanger, we can apply the first principle of thermodynamics. So it's an open system. We consider it as steady state, and we'll take as system the working fluid, so the refrigerant between the inlet point D and the outlet of the evaporator point A. So we can write, so if I write here in power, so in watts, the technical work in terms of power between point D and point A plus the heat power exchange between point D and point A is equal to the mass flow rate of the working fluid, so of the refrigerant. Here we need to be accurate about this because in the heat exchanger we usually have two fluids. So here I'm speaking about the refrigerant that will do the force transformation inside the machine, multiplied by the variation of specific enthalpy between point D and point A. So that's just the basic writing of the first principle of thermodynamics. In a heat exchanger, there's no technical work exchange because there's no moving parts. Doesn't mean that there's no work exchange because there's a work of insertion and of extraction. This is due to the fact that we have the same pressure at the inlet and outlet, but we don't have at all the same specific volume. So these two work are really different, but they are taken into account inside the enthalpy with the internal energy. So there's no technical work exchange, and what we are looking is Q coils. So the heat exchange that we have between the coil source and the refrigerant, and it directly corresponds to QdA here, and it can be calculated with the mass flow rate of the refrigerant times this difference of enthalpy between point A and point D. So the specific enthalpy of point A is always bigger than the specific enthalpy of point D. So this heat exchange is always positive. This is due to the fact that the refrigerant fluid receives heat from the coil source in this heat exchanger. Q hot now. So that's the heat exchange with the hot source in the condenser. We can do exactly the same analysis. It's a heat exchanger, so there's no technical work exchange, and the heat transfer from so the inlet of the condenser point B to the outlet point C is equal to the mass flow rate of refrigerant times the difference of specific enthalpy across this heat exchanger, so HT minus HB. This time HB is much bigger than HC, so we have a negative value for QBC because the working fluid is giving heat this time to the hot source. And then finally, what we want to know is the technical work of compression. And we can apply once again the first principle of thermodynamics. The technical work, so between inlet and outlet of the compressor, is between A and B, plus the heat exchange between A and B is equal to the mass flow rate of refrigerant times the difference of enthalpy we have across the compressor. And the compressor, even if we take into account the irreversibilities that may occur, we can most of the time consider that the compressor is adiabatic. So that means that we can neglect this heat exchange, and so the technical work exchange is directly equal to the product of the mass flow rate of refrigerant by the specific enthalpy difference across the compressor. Of course, HB is higher than HA, so it means that we have a positive value for this technical work exchange, because the working fluid needs to receive some work from the compressor. And that's it, because that's the only three components that are exchanging energy in this system, at least when we look at it at steady state.